Welcome everyone, and thanks for joining this tinyML global talk. My name is Gianmarco Iodic. I'm the chair for the tinyML global meetups. And today I have the pleasure to moderate this talk where Francesco Paissan, researcher of the Fondazione Bruno Kessler, is going to talk about designing efficient neural architectures and scaling strategies for edge computing. So Francesco today is gonna explain to us best practices, strategies to deploy machine learning models at the very edge, where you have important memory constraints along with energy constraints as well. Before we start with the presentation, with the talk, just a bit of housekeeping. So let's move to the first slide. Okay, and the first slide is to thank our tinyML strategic partners for making this event and many others around the world, virtual and in person, possible. I'd like to express my gratitude on behalf of the tinyML Foundation to AIZ, Arduino, ARM, BrainChip, Edge Impulse, Efficient, Green Waves Technologies, Gravity Inc., HiMax, ImageMob, Infineon, Inaterra, Note AI, NXP, PNG, PIMIC, Pauling Technology, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, ST Mechatronics, Synaptics, Synchance, and TDK. So the tinyML community is growing. Of interest, is growing in terms of technology around us. And absolutely the best place to be right now is in our meetup groups, because here which is the place where you can learn from the experts the best practices in deploying machine learning models or AI applications at the very edge. Here we're talking about devices with a very important memory and computational constraints, but with gigantic opportunities to unlock in new use cases very close to us. So in terms of the meetup groups, we have over 17K members already, with 49 groups in 41 countries, which is absolutely a great number. But we also have the community on LinkedIn, which is growing as well. So where can I find this talk and the others that the tinyML Foundation promotes and gives the opportunity to present worldwide? Well, certainly on YouTube. On YouTube, we have already 11K subscribers. We over 600 videos uploaded, where you can learn tinyML from a very basic presentation, where they explain the technology and best practices to start developing tinyML applications, to more advanced solutions, cutting edge implementations, to make unique applications with tinyML. Here we have also put a QR code in case you want to subscribe. This video will be uploaded on YouTube tomorrow. Before we start, just also some remark about the next events that in the area of tinyML and Tiny AI. In particular, we're going to have a live webinar the 5th of December 2023, so this year, on Tiny AI. So Tiny AI for predictive maintenance and anomaly detection. So it's something that you definitely should attend, in particular if you're interested in this area. And the event is, the registration is free of charge. The other two important events are the following. So the first is the tinyML Research Symposium, which will be the 22nd of April, 2024. Which will be held in the US. And the following days, we'll have the tinyML Summit. So the 23rd to the 24th of so honestly, I'm looking forward. I'm gonna attend the event. As always, I mean, it's gonna be a great event, because I'm pretty sure I'm gonna learn from the many developers around the world that are gonna participate to this event. The other thing, what to remind is the 2023 Edge AI Technology Report, the free report. You can download directly from the link, from the Wevolver link. So in case you haven't done it yet, you can download it to learn the latest technologies in the area of machine learning at the edge. So it's absolutely a report that represents the state of the art in terms of hardware and also software technologies to make machine learning possible on edge devices. We're approaching the beginning of this presentation, so just a few reminders. So as mentioned earlier, the presentation will be uploaded on YouTube, so we're available tomorrow, along with the slides in a PDF format. You can ask the questions, so of course, you can use the Q&A tab in Zoom to post your questions. We will try to address your questions during the presentation. In particular, note that Francesco has some checkpoints during his talk, and we could use these to address your questions you're going to ask during the presentation. With this, I think it's time to introduce Francesco Paissan. Francesco has been researching in the energy efficient embedded digital architecture unit in Fondazione Bruno Kessler since 2018. His research interests include diverse topics, from developing and modeling scalable neural architectures for multimedia analytics to biosignal analysis with deep learning architecture. In 2021, Francesco joined the Legend experiment for the design of novel physics-inspired machine learning algorithms. Francesco was a research intern at the Montreal Institute of Learning Algorithms in Montreal, where he worked on interpretability techniques for neural networks. It is my pleasure to introduce Francesco, and I'm looking forward to learn from you.
Thanks for the kind introduction. As Gianmarco said, today I'm going to talk about designing and feature neural architectures and scaling strategies for edge computing. In particular, this is the outline of the talk. First, I'm just going to give you a really brief introduction on tinyML, because I assume that since you were reached by these talk notifications, you probably are already familiar with tinyML. Then I'm going to introduce some concepts from the literature that help us understand some of the contributions from recent works in neural network design for efficient neural architectures. I'm just going to briefly talk about some scaling strategies as well. And then I'm just going to showcase some of some image and audio-based applications that we in E3DA deployed using our tinyML pipelines. So let's start with the 5 - 1, the W's of tinyML. So tinyML is, as you know, a fast-growing subfield of machine learning that targets on-device and near-sensor processing. And it's really useful because of its many practical benefits. For example, bandwidth reduction, because you don't have to stream the entire input data, or infrastructure sustainability, because if it's energy efficient, then you don't have to switch batteries so often. And also its scalability principles. Another side benefit, which is also really important nowadays, is that tinyML enables privacy by design applications by allowing algorithms to run directly on device, and those sensitive data never leaves the device and is not susceptible to man-in-the-middle attacks or vulnerabilities of that sort. It's not clear, at least to me, when tinyML started. I mean, we know when the tinyML foundation started, but tinyML was more kind of a process, and it can be, as in some applications, real world applications, driven by the necessity to be actually efficient in deploying some of the neural networks. And then the most important one, who is developing, here I'm focusing not on who is using tinyML because it would have been too broad, but more on who is developing the tinyML technologies. And I divided tinyML researchers and practitioners in two main categories. The first one is the tiny AI researchers, let's say it this way. This category mainly focuses on tiny machine learning as a machine learning problem. Focuses on compression algorithms, simplifying neural network models, novel quantization strategies to preserve performance while being much more memory efficient. And so this kind of high level problem definition. Whereas the second group that I'm identifying is the AI embedded engineers, which are more focused on the hardware aspects of tinyML, and approach tinyML as an engineering problem of making inference much more efficient using neural network accelerators or maybe neuromorphic processors as well. Of course, like as everything in life, is not all black and white. And in fact, there is a lot of stuff happening in the gray area with machine learning solutions being developed and deployed specifically for their scalability and adaptability capabilities on edge devices and vice versa. So now I'm just going to briefly talk about the challenges of tinyML. Again, I'm just going to be really brief because I assume that you already know stuff, but in case we can just stop and answer some questions. Of course, one of the main challenges of tinyML is the fact that you need to work with really low budget in terms of computational resources, and I'm talking RAM, of course, parameter memory, and also the speed of processor is not so high. So if you have a really high number of operations, then what will happen is that the inference will be really slow, and so you might lose real-time performance. So one of the first challenges of tinyML, maybe the main one, is to be able to work with efficient, both in computational terms and in energetic terms, platforms. And just for a comparison, here I put in the slides, we're talking about 10,000 times smaller resources than a workstation on which common machine learning and deep learning algorithms are trained on. In particular, generally, the target of tinyML are microcontrollers, single board computers, maybe neuromorphic processors, and which are all characterized by small parameter memory available in the range of kilobytes to megabytes, few operations per second. We are talking in the range of millions of operations per second, a small working memory, again in the range of kilobytes to megabytes. And one last constraint, which might be overcome also, but I think I wanted to include this because I think it's pretty relevant, which is the limited operation supports. In fact, generally, tinyML pipelines are usually optimized for a limited set of operations, and usually are focused on convolutional neural networks. Which is not to say that if you want to implement a custom layer, you cannot. It's just the fact that it might not be as optimized as other operations as well. And this is something that you need to take into account while developing and deploying tinyML applications. So now I'm just going to zoom out for a bit and not focus on Tiny anymore, because I want to just give you a brief outline of some papers in literature, in recent literature, let's say, that were really important for the development of also tiny architectures. And the first one that I'm going to talk about is AlexNet. AlexNet is, as you might know, a really old architecture. It was developed in 2012. And I'm saying old because it's now outperformed basically on every benchmark. But it was really important because it showed that convolutional neural networks can solve real-world problems. And in fact, AlexNet was one of the first breakthroughs on the ImageNet dataset, which is quite a challenging dataset. The architecture of AlexNet is composed by a sequence of convolutional blocks, which are depicted in the illustration on the slide, which are basically a sequence of convolutions with a set kernel K, a non-linearity, and eventually a downsampling layer via max pooling. So this is a really simple architecture. It's just a sequence of these easy convolutional blocks. Yeah, and the only takeaway is the fact that it showed us that CNNs can solve real-world problems, which is something that, of course, now we take for granted, given the performance and the tasks that we solve with CNNs. The next big step was ResNet, at least for the purpose of this outline, in which the authors showed that by introducing skip connections, it was much easier to train deeper models. Just to give you some notation, because it might be useful also to grasp some of the details later on in the presentation. When I'm talking about skip connections, I'm referring to this branch of the computational graph that you see on the slide. So basically, a skip connection connects the input and the output of convolutional block via an element-wise multiplication, addition, or maybe a concatenation operation. Again, as all CNNs, also ResNet is a sequence of convolutional blocks, and in particular, ResNet's convolutional blocks are residual blocks, meaning that they present this residual connection between the input and the output of each block. One thing that I want to draw your attention on is the structure, the channel structure of these blocks. In fact, residual blocks can be simple, meaning they are just a sequence of convolutions and with a skip connection, right? Or can be, let's say, a bit more advanced, more complex. And in particular, which is the illustration on the right, in particular, what I want to emphasize is the fact that for this kind of residual blocks, the channel structure is wide, narrow, wide, meaning that the input tensor has a high number of channels that gets reduced inside the convolutional block to be expanded at the end of the convolutional blocks just before resolving the skip connection. In this talk, I'm going to refer to this structure as the wide, narrow, wide channel structure. So many channels, you go inside the convolutional blocks, you decrease the number of channels, and then you increase the number of channels back. For this projection and expansion operations, we use generally pointwise convolution, so the kernel is 1, both for projection and expansion. The next breakthrough that I would like to emphasize is the one of MobileNet. Of course, many of you might be familiar with MobileNet, which tried to propose a much more efficient way of training neural networks. Actually, not training, but much more efficient convolutional neural networks for image processing tasks. So basically, what MobileNet does I'm just generalizing here. I'm not focusing on any specific MobileNet version because it's outside the scope of this presentation. You can just think about MobileNet as the paper that introduced the inverted residual block for efficient processing via CNNs. And the reason why it's called inverted is the fact that the channel structure is inverted. So instead of being wide, narrow, wide, we have a narrow, wide, narrow channel structure. Additionally, MobileNet is not just this. Additionally, MobileNet uses groups inside the main convolution of the convolutional block in order to be more parameter and operation efficient. So just to put this into context and with some illustrations, here is on the right a standard residual block, like similar to the one that we just discussed above. So you have a big number of channels, then you do your one-by-one convolution, you compress, you run your main convolution. In this case, it's adaptwise. It might not also be adaptwise. That's arbitrary. And then you have your expansion convolution, and you go back to the original number of channels. Whereas what happens in MobileNet is the opposite, right? So we have a small number of channels that gets increasing, so it's like narrow, wide, and then with the projection convolution, you go down again to the original number of channels, eventually multiplied by a width multiplier. So this slide here is just to emphasize the difference between the residual block, like standard residual block, and the inverted residual block. One last difference between the ResNet block and the MobileNet block is in fact the depthwise convolution that can also be applied to any residual block anyways. Another small thing that we're gonna anyways rediscuss later on in the presentation is the fact that if you paid attention in this slide, there is two variants of the inverted residual block. There is a variant in which we do have a skip connection, so is in fact a residual block, and another variant in which we don't. And the reason why the skip connection is not there in the rightmost computational graph is the fact that we have stride, so the input resolution of our tensor gets divided by 2 in this case. Of course, this is a problem because, as I said at the beginning, a skip connection is generally an element-wise operation. So if the number of elements is different, then we're not going to be able to solve the skip connection. Okay, let's see. Wait. I'm having some problems with the slides. Just a second. I'm having some problem with the slides. I will try to share the screen again. Just a second. Okay, you should be able to see the slides again, I guess.
Yes, yes, I can.
Okay, perfect. Yeah, sorry about that. Not sure what happened. Just give me one more second. Yeah. So, yeah, so I presented the inverted residual block and the differences with the residual block, just to recap a bit. And here, just to put stuff in perspective, I took this really old plot in which is missing many new and novel architectures, just to showcase what we're talking about in terms of trade-off of accuracy, in this case on the ImageNet benchmark, and number of operations in terms of multiply adds, millions of multiply adds. And also, just to give a reference, like when deploying neural networks on, like, for example, on an ARM Cortex M7 MCU, we generally target 200, maybe 250 millions of multiply add. That would be more or less at half of this x-axis, right? So you can see a clear trend between the complexity of the model and the performance, in this case for image classification, with ResNets being here. This is a ResNet 50, meaning that it has 50 layers, and all the different MobileNet and let's say more efficient architectures being studied in this range. So maybe we can just stop for 1 minute and see if there are some questions about this, and then I'm just going to introduce one more background slide, and I'm going to start with the contributions of our work.
Absolutely. So there are no questions right now. So let's wait a few seconds if we have questions in the Q&A tab. If not, you can continue.
Okay, sounds great.
Okay, it seems there is a question in the queue. Okay, so the question is, what is D-wise conv, which is probably depth-wise convolution?
Yeah, exactly. In the illustration here, it's just a depth-wise convolution, meaning that the spatial kernel is applied to all the channels, like the same spatial kernel. Sure. The reason why I'm calling it a wide, narrow, wide structure is because the number of channels, like images, for example, have spatial like height, width, and the number of channels for RGB images is 3, for grayscale images is 1. And then what generally happens during the computational graph of CNN is that the spatial resolution decreases and the number of channels increasing, of course, depending on the structure of the CNN that you design. In particular, for this block here, I'm calling it wide, narrow, wide, because the initial, like the channels, number of input channels for the input is higher than the number of channels inside the convolutional block. And just to clarify that, like as soon as the tensor enters the convolutional block, we are performing a pointwise convolution to decrease the number of channels. Then on the representation with a decreased number of channels, we run the spatial convolution, and then we project back to the higher dimensional space. And that's why it's called the wide, narrow, wide. Also, just a notation perspective is the fact that in neural network scalings for CNNs in particular, when you refer to a wider network, is a network with a higher number of channels. So wide, narrow, wide, meaning that the number of channels is higher, then it goes lower, and then it goes back, in this case, to the original dimension.
Okay, so there is another question about whether this presentation will be recorded. Absolutely is recorded and will be uploaded on the YouTube tinyML channel tomorrow. Right. I think you can continue, Francesco.
Okay. Thanks. Okay, so one last bit of background before we go on with the contribution, and is a paper of efficient. For the sake of this contribution, like for the sake of this presentation, the only thing that I would like to outline about EfficientNet is the fact that they did a pretty good study on neural network scaling, right? You might have heard of compound scaling, which is the scaling strategies that suggests that you should scale all the dimensions of a neural network at the same time in order to avoid diminishing returns. So again, and this also maybe is helpful for answering the questions that that we just discussed. The 3 ways of scaling neural networks that they studied in the EfficientNet paper are width scaling, meaning that you increase the number of channels, depth scaling, meaning that you make the network deeper, and for that, for example, residual skip connections are really useful. And then in the EfficientNet paper, they also talked about resolution scaling. Of course, all of these 3 scaling axes, let's call them that way, are relevant also for tinyML because they have an impact on the number of operations and parameters of the neural architecture. However, what we generally do, this is just out of our expertise in E3DA, is that we don't play with the resolution too much when deploying tinyML architectures. We prefer to focus on the neural networks instead. So just to summarize, again, the slide, EfficientNet proposed compound scaling. So you scale all these 3 dimensions at the same time, and you get the highest performance for the computational budget. So here I just wanted to highlight some of the shortcomings of the mainstream CNNs that I just talked about. First one being that they are too demanding. So as I showed you in the plot just before, these neural networks, even the most efficient one, like for example, Binet and EfficientNet, might be too demanding in terms of computational complexity, in particular in terms of parameter memory or RAM usage. because for inference time you can just wait if your application allows that, then you don't have to run real-time inference, you just wait longer, but at least you are able to run the inference. So this is one main drawback of these CNNs that I just talked about. Another one is the fact that they are not designed to exploit the capabilities of different edge devices. As you know, also by looking at the sponsors of this event, there are many platforms that you can target for tinyML, and they are all slightly different in terms of what they are optimized to run and optimize it. So the point is, like, if you just develop let's say general CNN and you don't focus on hardware experimentation, you might end up with a network that is good in terms of parameters and operations, but it's not exploiting all the capabilities of the device. And the other thing is the fact that we just talked about this compound scaling changes all the computational axes in a coupled way. So what I want to say by this is we saw that compound scaling tells you that you should change the number of channels together with the number of layers, together with the input resolution of the neural network at the same time. Of course, this has an impact on all the computational requirements of the neural networks, so both the parameter memory, the working memory, and the number of operations, which is something not desirable, because if you just want to slightly tune the neural network to optimize just one of these, you might be in trouble. So here, actually, I see there are 2 questions, so maybe I can stop for a bit before going on. Sure. Could you please elaborate on compound scaling? Yeah, let me go back to the other slide. So without going into the math, which is anyway pretty simple. So if you refer to the efficient paper, I guess the intuition might be clear. The intuition of compound scaling is just the fact that you don't want to scale one dimension at a time. And by this, I mean, if you want to make a neural network bigger, making it just deeper, so adding more layers only, will give you diminishing returns. So your performance will increase, but then they will plateau almost right away. And the same happens if you just increase the number of channels. So you keep the depth of the neural network fixed and you make it wider, you will again see diminishing returns. There is also a trend with the input resolution. So if you just fix the neural network to a specific configuration, so let's say a certain amount of channels for each convolutional block, a certain amount of convolutional blocks, and you just increase the resolution of the image, what will happen is that also the performance of the model will change, but you will see again diminishing returns. So what the authors of EfficientNet proposed as compound scaling strategy is a scaling strategies that scales, like, changes all these 3 dimensions at the same time. And what they saw experimentally is that if you do so, you will plateau later on in terms of performance, and so you will be using getting the most out of your scaling regime, basically. I'm not sure if that was clear enough. But in case, also feel free to just drop an email or just ask again later on in the presentation as well. Next question is how to compute whether the RAM of a specific core is powerful enough for a given CNN. For this one, let me go on with the presentation, and then if it's not clear, we can answer it at the end of the presentation or also on the forum. So I will just resume the presentation, and then we can just keep this here, and let's see if it's answers by itself during the presentation. So what I wanted to tell you now is the qualities of an ideal CNN for edge processing, which is of course a CNN that has that can scale to low computational complexities. so can adapt also to different neural architectures. And we're talking architectures with lower than 1 million parameters encoded in unsigned int8, and with less than 1 megabit of RAM. Also, its convolutional blocks of this ideal CNN should be designed to exploit all the resources maximally. And I'm talking about also the accelerations that different platforms provide. And then just the cherry on top would be to have a scaling strategies for this neural network that allows you to change these computational requirements and fine-tune them to adapt a neural network directly for a specific edge device. So let's say maybe you develop your neural network for an ST device, and then you have to deploy your application on also another device, maybe a green waste device. You will just run this scaling strategy, and it will magically give you a really good network for that device as well. So this is what ideally would be good. At least that's what I think it's a good goal to go towards. So with this, I would like to introduce the first contribution of this that I'm going to describe in this talk, which is FiNets, which is a convolutional neural network based on inverted resolve blocks. So it follows the narrow, wide, narrow channel structure, which are slightly modified to decouple the computational resources, which is exactly what we would like to do, and what compound scaling does not allow to do. Also, this neural architecture is designed and optimized for multimedia analytics. In particular, we worked and benchmarked this architecture on both audio and video applications, as you will see later on, also in the application sections. The last point about FiNet is the fact that you can control the RAM, flash, and number of operations using the 3 hyperparameters that you set in the code, for example. So what those 3 hyperparameters do, we will see it in just a bit. What I would like to point you towards is just the fact that with FiNet, what we try to do is like maximizing the scalability that a CNN can have, and then see if some cool behavior emerges by doing so. So as I just said, the FiNet's convolutional block is an inverted residual block, meaning that it follows the wide, narrow channel structure. And just to recap a bit, just to make sure we are all on the same page, it's called this way because you have an input tensor, then you have an expansion convolution that increases the number of channels, and the number of channels that it will be increased to is computed using this formula, which is a function of the actually all 3 hyperparameters, because we also have the number of layers as well, which is arbitrary. You can always change the number of blocks. Then you have your main convolution, which in this case is a depthwise convolution. We also tested with a squeeze and excitation block, which can be considered a form of attention mechanism, a really simple attention mechanism. And then at the end of the convolutional block, we have a projection convolution that projects the number of channels back to the input number of channels. And so at the end, you can also compute a skip connection because the dimensionality of the tensor is the same as it was for MobileNet. If you are performing downsampling, which generally happens in the depthwise convolution, then you might not be able to solve the skip connection. There are some tricks for that as well. Maybe we will see some later on in the presentation. So this is just a convolutional block. But if you take one of these and like you take many of these convolutional blocks and you put one after the other, what will happen is that you will create a FiNet, basically. And one of the main characteristics of FiNet is the fact that the expansion factor, meaning that the number of channels to which you are expanding towards, linearly decreases with an increasing number of layers. So you start with a base expansion factor of T0, meaning that if you have 3 channels as input, then the output of the expansion convolution will be 3 times t. Then you will run your depthwise convolution, and then you will go back to 3 again. If that's the case, I mean, you can play with the configurations as you see fit. But the important thing to note is the fact that the expansion factor goes from t0 to beta times t0. So there is a linear scaling in the expansion factor. And this is one of the reasons why finite is much more efficient than mobile and efficient, despite being based on inverted residual blocks as the other architectures. So here is just some advertisement. We are wrapping all of this tinyML neural networks inside a Python package, which is PyTorch based, and it's called Micromind. I have a slide at the end with some details. But if you're interested in using Finet or Xinet, I invite you to check out the GitHub or the Python package itself. We also provide some pre-trained checkpoints for image classification and object detection. It's still in beta, of course, is work in progress. But I will just put here some pointers. So also maybe next days, if you want to just check out the slides, you have the reference to where things are inside our toolkit. So maybe just I will stop also here to see if there is any questions about the finite convolutional block or the finite architecture in general. So
Absolutely.
we're on the same page.
Yeah, let's wait a few seconds if there are questions about this part. Okay. If not, yeah, there is one question. Yeah. What part of the architecture brings the best benefit?
Okay. So let's see. There depends with respect to what, right? Because if you are talking what would be the benefits with respect to a vision transformer is just the fact that the operations that we run are much more efficient because we don't have to compute all the attentional kernels and stuff like that. But if you talk about, for example, MobileNet, which is a much closer architecture in terms of what it's been developed to do and to be used for, since the convolutional block is really similar, right? It's based on inverted inverted residual blocks, right? So we have pointwise, depthwise, and pointwise again. The main contribution and the main reason why Finet performs better, and we will see some numbers later on in the presentation, is the scaling approach that we are using. So the fact that also thanks to that linear scaling of the expansion factor, you can play with different finite configuration much more easily that you can play than you can play with EfficientNet or mobile. So it's much easier to play with one dimension at the time instead of just scaling all dimensions simultaneously. And Finet was developed exactly for this. In fact, one of the benefits of Finet and also the next architecture that I'm going to talk about is what we call algebra-aware scaling. There is also a slide about that in the presentation. But the main benefit in general of both neural networks that I'm presenting today and all this paradigm that I'm trying to use to approach these problems is the fact that you can design one architecture for each platform by having a really scalable architecture and knowing what each hyperparameter changes, such that you will also be able to let's say, double the RAM or make the RAM half what it was before without also changing too much the other computational axis as well, which is something that you cannot do with MobileNet, for example. MobileNet just has one hyperparameters, and plus you can change the number of blocks. So it's just much harder, and it needs much more handcrafting to be deployed on many different platforms. So maybe that's one of the best benefits that we have. And then in terms of, given this, of course, in terms of performance complexity trade-off, we are much better off than MobileNet, EfficientNet, and other architectures as well. So this is just to say that in this case here, we did not develop any novel convolutional block. It's more how we used the inverted residual blocks that makes the efficiency, which is not the case for. I mean, it's also the case, but there is also more novelty in the other approach as well. I hope this answered the question.
There is another question about, as a developer, is all of these things you have just described already integrated in available tinyML frameworks?
So let me read it again. I mean, this is a tricky question because my answer is, of course, yes. You should care about this because knowing these things, of course, it depends on the depth at which you want to know stuff, right? And knowing stuff much more in detail might allow for further optimization, meaning that your application might run faster or with higher performance or something like that. Another thing that I would like to point out is like what I'm presenting today are all research approaches. And so they are not developed to be safe, to be like super safe. They are never wrong. We are trying to push the state of the art. So generally, the approaches that I'm presenting today are much better in terms of performance than current state of the art approaches. And I can also tell you for a fact that both these architectures that I'm going to talk about are not available in other tinyML frameworks other than, of course, Micromine. But anyways, just it's something that you might want to know, but it's up to you. Like, if you have any more specific questions about this or any detail that I missed, then I would be happy to answer that as well.
So there is another question, but not sure if you want to address now or do you want to address later. But what?
Yeah, I mean, it's pretty fast, so maybe I can do it right away. So as I told you, the finite convolutional block is using inverted residual blocks. So it expands the number of channels, right? So with this expansion convolution, what's happening is that we are increasing the number of channels before performing the depthwise convolution. And what is reducing in the sequence is exactly this expansion factor, meaning that if at the beginning of the network, your expanded number of channels is 100, then at the end of the network, it might be 3 or 5 or 10, depending on the hyperparameter beta that you set at the beginning. So going deeper inside the network, you will increase the number of channels less in the expansion convolution. I hope I answered the question in case.
Okay.
Just
thanks,
okay.
Francesco.
Okay. The other thing that I would like to point out, anyways, is the fact that finite, same way as MobileNet or EfficientNet, or many other applications, neural networks that are designed and developed specifically for tinyML, have the problem that are based on indirect efficiency metrics. And by indirect efficiency metric, what I'm saying is that for finites, as for MobileNet, EfficientNet, what we try to optimize is the number of parameters, the amount of RAM, and the number of operations. But of course, depending on the hardware platform that you're running your tinyML application on, the number of operations might translate to a different efficiency or to a different inference time, depending on which operations you're running and if those operations are accelerated on a specific hardware platform. So what if we try to just measure this efficiency instead of basing the design decisions on this proxy metrics? What would happen? Like, what would a convolutional block look like, or an efficient neural network designed that way? So here's where first let's define what we mean by efficiency in this slide here. Efficiency from now on in the presentation is the factor between a specific amount of energy to run any operator, and by operator I mean different layer in a neural network, with respect to running a standard convolution. So not a group convolution, not a pointwise convolution, just a 3x3 convolution. In particular, we chose the 3x3 convolution because empirically, and we know that these operations are the most common one in CNNs, and they are also the ones that hardware vendors optimize for when optimizing for efficiency and accelerating neural network inference. So what we did is, like, after defining this efficiency metric, we took a bunch of different hardware platforms that are in the realm of used in the realm of tinyML applications. So I'm talking boards from ST, Greenwaves. We have also another RISC-V architecture, the Kendright K210, with also a specific accelerator for CNN inference. And then what we did is, like, we deployed each layer individually on all these platforms, and we measured the efficiency for each platform and each operator. The outcome of this benchmarking is what you see in the lower part of the slide. You can see, of course, each bar group is a different neural network layer among the most common one that you can find in both CNNs and CNNs applied to generative tasks. So transpose convolution, nearest neighbors, and bilinear upsampling or depth to space. As you might observe, of course, come to the have a 100% efficiency, because that's the definition of efficiency, like the energy over the energy for a come to D. And it's clear by looking at this plot, the fact that the best convolutions, after all, are 3x3 convolutions, followed closely by pointwise convolution. And I mean, those are the two clear leaders of this ranking, right? Which is funny because, I mean, we went all fancy with depthwise convolutions, and then it turns out that what AlexNet was doing in 2012 might be the best thing to optimize efficiency. Just for a reference, as we discussed before, both FiNet and MobileNet, MCUNet, or many other tinyML-oriented architectures are based on depthwise convolutions. So it's clear here that COMP2Ds and pointwise are the best choice if you want to design a custom convolutional block that explicitly optimizes for what the hardware platforms are able to do, and to do efficiently. But there is a main concern about this, which is the fact that, as you know, 3x3 convolutions don't scale so well with the number of input and output channels. And this is the reason why depthwise convolutions and grouped convolutions in general are the preferred choice for parameter-efficient architectures anyways. But what we try to question in the work that you find in the reference here is there a solution to solve this problem of parameter and memory efficiency while using these really efficient neural operators? And it turns out that if you are clever enough in how the way you arrange the different operators inside a convolutional block, you might get something that is really efficient also in terms of RAM usage and parameter memory. So what you see in the slide right now is the XiNet convolutional block, which is composed by only 3x3 convolutions and pointwise convolutions, because they are the most efficient operators that we benchmark, that we found out from the benchmark. And since the idea is to reduce the complexity, also intuitively, what you might think is that compressing stuff is a good idea. And that's exactly what the excited convolutional block does by following a wide, narrow, wide structure for the number of channels, similarly to what the residual block was doing, is doing actually, is still doing. So what you can see is like the input tensor, it's like the number of channels of the input tensor is decreased by a factor gamma with this compression convolution, which is a pointwise convolution. Then we eventually run a skip connection that I'm just going to describe later on. And then we run the main convolution that works on the spatial domain together with the channels, which is a 3x3 convolution, which output number of channels is the output number of channels of the convolutional block. Then this can be followed arbitrarily by an attention module, which is also that we also designed, and I invite you to read the paper for all the details, with the same two operators, just to maximize efficiency. And of course, then you have the output of the convolutional block. So if you take a closer look to this illustration, you see there are two blocks that I just skimmed over, which is the broadcast skip connection and the attention module. I'm not going to describe those in detail. The only thing that I would like to say about this is the fact that for both skip connections and the attention module, we use the same 3x3 convolutions and pointwise to maximize efficiency of the overall architecture. And also we ran an experimental study to see where the skip connections are better for the performance complexity trade-off. And what we found out is that if you take the skip connection from the output of the first convolutional block and you connect it to all the different blocks throughout the later blocks in the CNN, you will get the best performance for a given complexity budget. Of course, this poses some challenges because, as I was saying at the beginning, if the dimensionality of the tensor is different, then you will not be able to solve the skip connection. So you need to play with the dimensionality of the skip connection tensors by doing, in our case, a pointwise convolution to fix the number of channels and an average pooling to fix the spatial resolution. And then we did a similar analysis for attention as well. And this is quite a bit more complicated, so it would be not so meaningful to go over now. The only point, again, is the fact that it was developed given the harder benchmarking. So just to summarize what AXINET is composed by a sequence of AXINET convolutional blocks, which is what we just saw. Similarly to FINET, it uses three hyperparameters, alpha, beta, and gamma, to control the computational requirements of the network such that you can scale the architecture in the computational constraints space. And it's designed on based on an empirical benchmark with of different operators on different hardware platforms with different accelerators as well. Same as for FINET, you can find the code for this architecture and some checkpoints as well on the Micromind repo and Hugging Face profile. It's again also this is work in progress, so we are adding checkpoints in these days. We will also support more neural architectures. We were planning to include MCUNet, Micronet, and other tinyML oriented neural networks. Last thing about methodology is hardware-aware scaling. I just briefly, because we already talked about this, hardware-aware scaling is a neural network scaling strategy that instead of doing the same thing that compound scaling proposes of changing all the dimensions at the same time, focuses on changing one dimension at a time to maximize the occupation of RAM parameters and operations for a specific hardware platform. Okay, so just if there are, since we are I'm being a bit slow. If there are any questions, and then otherwise I will just go quickly over the applications.
There are no questions for now. Let's wait a few seconds. I'm also conscious of the time, so I would say let's continue. Let's see if we have questions for the end.
Okay. So I will present you two applications that we solved using both FiNet and XiNet. One is for images, and we decided to use a YOLO pipeline just because it's general. It solves a bunch of different tasks, but it's not the only application that we developed. We deployed FiNet and XiNet to. And the other one is zero-shot audio classification, just to showcase how FiNet and XiNet can also perform well for audio processing tasks. So YOLO is for you only look once, is an object detection pipeline that was originally well known for its good performance complexity trade-off. When I'm saying good performance complexity trade-off, I'm comparing it with other approaches that were using like region proposal networks. So they had two steps for each image, one to detect the interesting regions, and the other one to verify if something useful is in those regions or not. Instead, what YOLO does, it just runs in one single inference, detects multiple objects in the frame. And so for this, it was much more efficient than other approaches. It was originally developed for object detection, but it was later expanded for image segmentation, key point detection, and also voice estimation. A couple of examples of YOLO outputs are here in the bottom. On the left part of the slide, we have the object detection, and for the right hand side is key point detection. So just to give you a brief overview of the YOLO architecture, the way the YOLO architecture is composed is using a backbone, so a feature extractor network, originally a darknet, followed by a NEC, a processing NEC, and an object and a detection NEC. Let's call it this way. So in the original implementation, the most concerning parts of the pipeline in terms of computational complexity is the backbone, because it's the one that needs to extract really good features. Otherwise, the entire task will not be able to be solved. Given this, an intuitive way to optimize the computational complexity of these object detection pipelines would be to play with the backbone and see if we can make a backbone which is more efficient than darknet, or and see how it performs, basically. I would like just to point out that also in the literature there are many approaches that try to simplify the task of object detection, like decreasing the number of channels. The number of channels, or decreasing the image resolution. Which is, I mean, it can be good for specific applications, but ideally what you would like to do is like make a really efficient object detector, and such that if you want to specialize that, it will be even more efficient than the really big, like the one solving the hard task. So the way we approach this, as I mentioned, is by changing the backbone. So we have two versions of, let's say, efficient YOLO, which is YOLO FiNet, in which the backbone is changed to be a FiNet. So we basically use a sequence of FiNet convolutional blocks for extracting features that will later on be used by the YOLO NEC and the detection NEC, which was originally benchmarked in 2022 against MobileNet and EfficientNet, both for object detection and object tracking. In this case, we are talking about tracking by detection, so the performance of the tracking are heavily relying on the performance of the object detector. We deployed this YOLO FiNet architecture on an ARM Cortex M7 MCU with only 2 megabytes of internal flash and 1 megabyte of RAM. and we achieved power power consumption in the order of 10 milliwatts for a 52% mean average precision for object detection. You can see the numbers for tracking as well in the plots on the VOC 2012 dataset. So one thing that I would like to point out, now it's a good point, also to recall the questions that we got at the beginning, is the fact that we do also have the recipe to reproduce these results and use the latest version of YOLO V8, which is even more advanced than the one that we extracted these results with. And to the best of my knowledge, there are no other repos for tinyML specific applications that also support the entire exportability pipeline all the way to the MCU with reproducible results online. So if you are interested in object detection and efficient object detection, I invite you to also check out this work. Then we did the same thing for YOLO SciNet as well. So we took the original backbone darknet, we changed it with a sequence of SciNet convolutional blocks, which is always the same story to make the object detection pipeline much more efficient. And it turns out that it's actually much more efficient. We deployed it on the same hardware platform as the previous approach. We reduced the number of operations by a factor of 2 with respect to MCUNet, and we decreased the number of the RAM usage of almost 10 times with comparable performance, that is. Also in this case, we evaluated the approach in terms of power consumptions. We are in the range of 20 milliwatts at almost 70% mean average precision on the VOC 2012 dataset. Same goes as before. If you are interested in this recipe, the same. This is a link. So if you have the slides, you can press a link. It will point you towards the code. Just one last thing is the zero-shot audio classification task. That's one of our most recent works, and it's actually under review at the moment, which is based on CLAP, which stands for Contrastive Language Audio Pre-training, which is basically trying to learn a similarity between audio and text in some shared latent space. And this similarity score can be exploited for zero-shot classification. What I'm referring to when I'm talking about zero-shot classification is the fact that you don't have a fixed number of classes, but you describe your desired class in text, and then that string will be compared to the input audio. And if there is a high match, then that's probably your class. Otherwise, it's another class. Like the text description and the audio don't match. So just quickly, what we are trying to do during training is to maximize the similarity score for pairs in which text and audio are matching, and minimizing the distance, the similarity score otherwise. And then what an inference pipeline would look like is that you have your own input audio, then you have a sequence of queries, let's say it this way, of text strings describing specific audio events. Then you run the text through the text encoder, the audio through the audio encoder, and you compute the similarity score for each of these queries. The query with the highest similarity score might be your actual class, and certainly is much more aligned with the audio with respect to the other queries in the set. This allows for classification in scenarios in which you don't have a clear understanding on which classes might be relevant. And so you might want to update these queries at runtime without having to retrain the entire model or run on-device updates. So our contribution here is basically a distillation strategy and a pruning strategy for contrastive learning approaches. We made the audio encoder much more efficient by considering the fact that the text encoder is fixed. So in a tinyML application, what we are expecting is the fact that you compute the queries, like the text encoding of the queries, on some let's say fog or cloud instance, and then you just stream the latent representations to be compared with the audio representation. And so we just focused on the audio encoder architecture. Same goes as for the other recipe. In this case specifically, you will have the link tomorrow. If you press on it, the code is not there because it's being refactored and fixed. But talking in terms of performance, similarly to what we observed at the beginning, the performance here follow up power law scaling behavior. Here we have 3 different data sets for audio classification: ESC50, TUT 17, and the Urban Sound 8K, with different number of classes. And you can see that depending on how you change the hyperparameters of your finite in this specific scenario, you will get different zero-shot accuracy performance. This was not yet deployed on any MCU. It's just a work in progress. But I would like to point out that we had a 94% reduction in parameter count with respect to the original CLAP, that is from 82 million parameters to 4 million parameters, which is anyway quite big with respect to the other architectures that I was talking to you about just before. But this reduction rate is just for the architecture that drops the zero-shot accuracy by 4%. So if you're in your specific application can allow for a slightly bigger drop in performance, then you're good to go, and you can have neural networks which computational constraints requirements enable to run MCU inference. Also for this, I invite you to check out the paper if you want further details, and eventually reach out. The last slide of today's presentation is just about Micromind again. Micromind is not a startup, is not a research project. It's just an open search project that we are leading here in E3DA, which tries to provide an entire pipeline for research in tinyML. And by this, I'm talking about having reproducible results from papers, mainstream papers in tinyML. That's why we are planning to add MCUNet, Micronet, MCU Former, and many other newer architectures that are specifically developed for tinyML. We also have already image classification at ImageNet scale implemented inside Micromind. We do have object detection on Coco and VOC, and we will in short time have the zero-shot audio classification code implemented. And the idea is like with Micromind, what we're trying to provide the community is a tool to develop and compare many different architectures before deploying them at the edge. So that concludes the presentation. If you are interested in Micromind, please check out the GitHub profile. And also, if you are interested in actually using it, just leave a star so we know that someone cares. And anyway, for further updates on this, you can follow me on X or Twitter.
Thanks a lot, Francesco, for your presentation, where I'm pretty sure we have it was absolutely well detailed about techniques to improve accuracy, reduce the memory consumption, and improve also the performance. I thought that we won't take questions because we are definitely at the very end of this presentation. But on behalf of the tinyML Foundation, I want to thank our speaker, Francesco Paissan, for presenting today. A reminder, this presentation is anyway recorded, and for the questions or any additional question, you can reach out directly Francesco, who is gonna be more than happy to help you. So let me proceed with the remaining slides of this talk. So as mentioned at the beginning, our big thank you goes to the tinyML strategic partners for making this event and all the other activities, events, virtual, in-person possible in the era of ML on edge devices. Let me see if I can control your screen. If not, can you go to the next slide, please? So in particular, in terms of executive strategic partners, we'd like to thank Qualcomm AI Research, Cynthians. In terms of platinum strategic partner, we want to thank Sony, gold strategic partners. We want to thank ARM, Edge Impulse, Infineon, Innaterra, Renesas, ST Mechatronics, okay. In terms of silver strategic partners, AZ, Arduino, BrainChip, Efficient, Green Waves, Gravity Inc., Himax, ImageMob, Note AI, NXP, PNG, PMIC, Pauling Technology, Schneider Electric, SensiML, Silicon Labs, and TDK. And this is our last slide for this presentation. Thanks a lot, Francesco, for the well-prepared and very detailed discussion about how to tailor architectures for memory constrained devices. With this, I'd like to thank also our attendees. I'm really looking forward to attending the next session and to welcome again. Bye-bye. Thanks a lot.